Okay, that did not work. Okay. Okay, update. I think we're actually live. Hi. Speeding at Seeds VC. Hello. Oh my god. I feel like every time I load up OBS, there's always some sort of crazy issue. But hi. Hi, class. I could just do quick attendance. Hello, Doc Rect. Hello, Hair Day. Hello, Eggy Nugget. Hello, Nikki Parafergon. Hello, Stella Curie. Hello, Germanium. Hello, Astral Chopos. Hello, Architelos. Hello, Karbon, who is actually with me. Hello, PodJam Subway. Hello, Nova. Okay, so with that, before we get started, Karbon, how about you go ahead and introduce yourself?
Hi everyone, I'm Karbon. I'm an astronaut VTuber. Whoa, I also do physics. I'm not as hardcore as Z, but I try to be. And I'm gonna be here today doing some space stuff with you. I'm another space lover. What can I say?
Oh, Karbon's sound is low? Okay, I think it's fixed. Testing.
All right. Testing. 1, 2, 3.
Is that better?
Hello.
Okay, now it is good. Okay, maybe you could just redo your intro if people weren't able to hear. Yeah.
Okay. Hello. Take 2. It's always better the second time. I'm Karbon. I'm an astronaut VTuber. I also do some science. I'm not as talented as Z, but that's okay.
What? No!
And I'm here to teach you some space facts today. I really love space, obviously, and we love some environmental testing so we don't burn billions of dollars. Or millions. Could be billions. Depends on how it fails.
Now, millions would be kind of scary to
Don't worry, everyone makes their first $1 million mistake in the aerospace industry. It'll happen to all of you.
Oh my god, well hopefully it will not happen to me in the near future, knock on wood. Oh my god.
Possibly. Anyway, I'm really excited because we've been trying to do this collab for a while now, but my goodness, content schedule plus real life schedule make it so hard.
Yeah, I mean, being IRL scientists just mean that things are just really busy, right?
That is true, yes. Oh, did I say that? I'm an IRL scientist. I do IRL physics. Woo.
IRL scientists squared, let's go!
Yeah.
Yeah.
We're very nerdy.
Well, yeah, no, I'm actually so glad that this collab made it out of the Discord chat, because we've been talking about this for a really long time.
Oh, when I first became a VTuber, I instantly found Z, and I was just like, oh my, someone's already breaking into the science VTuber scene. And let me tell you, it's a niche spot. It's a hard place to be, but she's making it work. So kudos to her. Clap, 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 clap,
Well,
clap.
thank you. Well, I know, Karbon, you also do like more general content too, right? Like gaming stuff?
Yes, I'm in the dregs of Twitch, so, you know, as the Twitch gods demand, I must play Monster Hunter. So that's what I'm currently doing.
Well, if you haven't already, I have linked Karbon's Twitch in the pinned comment, so go and subscribe. Is it still called subscribing?
No. Subscribing costs you money, all right? You follow, all right?
Oh.
Yeah. But feel free to stop by. We have a silly vibe. One thing that happens to me is when I do physics all day, sometimes I come home and I'm like, I need to rot my brain. But other times I come home and I'm really excited by a problem and I'm like, I need to rant to you for 3 hours straight about a really obscure physics problem. And I do both of those.
I feel like that's a great balance. I think like the chaos, sometimes the brain is like so saturated, you just need a little bit of brain rot to like cancel it out. Looks like chat is asking No Man's Sky collab in the future. Maybe we need to do a gaming collab now that we've done a science one.
Did Karbon ever play Kerbal? Oh yeah, I spent a lot of Z, I don't know what your experience was with Kerbal Space Program, but I launched something into orbit and then I was like, great, it's in orbit. Now all we have to do is wait for it to come back down because of like the photonic pressure is gonna push the ship over, and there's gonna be like atmospheric drag, and the ship will come back. Turns out it's a game. They don't simulate that sort of stuff. And my first couple Kerbals are stuck indefinitely.
Oh, sheesh. Okay, so my experience with Kerbal was I was like brand new to the game. I didn't even know what the controls were. I didn't even know like how to launch anything. So I got like
same here.
I got a lot of help from chat, which was great.
Okay.
But
Yeah.
Zasa, which is like NASA with a Z, has 100% survival rate. So I'm doing pretty well. Wait, I am planning
Wait, that's
to
not a meme.
Yeah, exactly.
Oh my gosh, I have currently I have like a 20%. I think I've that's really bad.
You're the one who's losing millions of dollars.
Nah,
And I guess
I'm also breaking headwind, okay? It's fine. The
Wait.
Kerbals, they can reproduce.
maybe we need to do a Kerbal collab sometime because I am planning to continue the series after my Zeducation schedule for the next week or so, which is I'm gonna put it up on the screen right now.
We're gonna be spending 40 minutes while actuallying each other till we get to the launch pad. That's what's gonna happen.
Wait, but
I
maybe
can already
that's how
see
it
it.
needs to work. Because I feel like I'm brand new to the game. I need somebody who is a master of the trade.
Let me tell you, I am also brand new to the game, and I was trying my best and causing things to blow up. I wouldn't call myself a master.
So maybe when we collab, the survival rate will go from like your 20% and then like my 100%.
We'll average
and
it. No.
It'll be like 60%. Or
You know what?
65%.
Acceptable range. It's
Yeah.
fine. That's okay. Yeah, totally. Kerbals are indestructible, don't you know?
Yeah, no, they have infinite lives. 120% survival rate. Yeah, that's more like it.
You're right. We'll send one up. We'll get two back.
Well, that's how it works. The first Kerbal reproduction in space.
That'd be pretty amazing.
Yeah. Well, I guess we should get started soon. But before we get started, just a quick announcement. I don't know if I will be doing my Astrobytes Journal Club this Monday. Depends. I have a lot of deadlines for grants and stuff coming up soon, so it's been a little bit of a crazy ride.
You can do it. I believe in you.
Thank you. So instead of doing the journal club, I might actually just work on my partial differential equation series instead, which I know that a lot of chat has been waiting a long time for. I have been finishing up the first video of the series. It's been taking a long time. And then this following Saturday, I am collaborating with my VTheorem genmate, Nep, who is a horticulturalist in real life and does horticulture content. So keep an eye out for that as well. Woohoo!
Ooh,
Okay.
let's go Nep.
Yay! Alright, do you want to get started?
Yes, I'm ready. I'm ready to get started.
Alright,
Let's go.
space environmental testing with Z and Karbon. Okay. So, oop.
Look at that beautiful ring thing. What's that?
Yeah, what is that? I wonder. Well, I guess I can just give a brief description of why do spacecraft need to be tested. Well, as many of you guys may know, space has harsh conditions, but it's
Understatement of the century.
I think Kerbal Space Program is a great demonstration of this. I mean, launch is really intense, and space is also very harsh. And so a lot of environmental and electromagnetic interference testing is really important to make sure that the satellite can make it to space, and even survive in space. And I guess the next slide, Karbon, you could talk about this.
So the second part of that is if space is really hard and extreme and things fail in space, why do we really care? It's because once you send something up to space, if it breaks, it's really freaking expensive. Like extremely expensive. If you click see,
Yep.
it is at least every single satellite you see right now for the Starlink internet satellite system, which is one of the cheapest satellites out there right now, is $1 million per satellite. And with their reusable rockets using the most cutting edge technology, is about $50 million per launch, which only fits about 22 sats. And that's a very expensive endeavor. If any of these satellites go down, that's a minimum of $1 million cost.
That's crazy. That is like absolutely insane.
And they go down regularly, mind you, by the way. So this is high stakes, to say the least.
How regularly do you think they go down?
Oftentimes they'll not have proper environmental test coverage. So maybe a new part from a vendor that they ordered isn't rated for the vacuum of space, comes up there and poops itself. It happens sometimes in big bursts where like 3 or 4 of them fail. Sometimes like 30 of them can fail at once. The entire launch is botched. There are times where theoretically, once it's up there, it doesn't fail. Once it's like set up and set to go, you've reached stable state. But the very first couple days after launch or even during launch, that's where most things fail.
Wow, I didn't even know that, because I thought that they tested these satellites really well, especially like
They do?
the Starlink ones.
Oh yeah, they test them really well, but that sometimes people make mistakes and it costs millions of dollars. It will be pulled back to, I mean, I know Starlink especially is a kind of a hardcore place. Each person has like a responsible part owner, so they will find out who's the responsible part owner who did not fully test their thing and come back and be like, hey, you bricked a satellite. What do you want to answer for that?
Wow.
A really great smaller scale is CubeSats that are launched very regularly. I don't know if chat knows what CubeSats are, but they're like small hobby level spacecraft that have an appointed NASA engineer / scientist who reviews the Cube satellite before its launch. So these have been reviewed by professionals who've done this hundreds of times. They still have failed test coverage all the time. You'll see in Wikipedia articles for hundreds of satellites where you look at it, they'll be like, oh, RF communication failed, or star camera failed, things like that. Like different components of the satellite will fail all the time and make data almost unusable. So it's scary. Big stakes.
I mean, and CubeSats, for context, are, how do I even explain this? They're like, I'm like trying to do it with my hands, but like I'm realizing that's not portraying very well. Maybe like the size of like a small, like a 2/3 of like a.
It's a Rubik's Cube.
I think it's a little bit larger than a Rubik's Cube, like a 1U CubeSat.
Yeah.
It's probably like a 5x5x5 Rubik's Cube. Yeah.
Yep.
Yeah,
so,
a 10 by 10 by 10 centimeter. Wait,
even
sorry,
those small CubeSats, they fail, and they're like pretty well designed. Like it's a very known way to make them.
Yeah, and these CubeSats have become a lot more popular nowadays. There's companies that actually can. There's this one company where they have like a giant like box, and inside that box they can fit like maybe like a dozen of these CubeSats. And when it's time, like the box is taken up in the rocket, the box like opens, and a bunch of CubeSats are just like ejected. And you can see them like at SpaceX launches, and they say like, "Oh, this CubeSat has been deployed."
Yeah, it's pretty good. What's the failure rate for satellites? I think it varies significantly between different satellite types. The reason why I use SpaceX in this example is because they are literally like 70% plus of all satellites right now that orbit the Earth, which is insane to think about.
Yeah, cluster launch. Yeah, no, that's crazy though. The prices to fail in space it's intense. That's why we need really good testing, right?
Oh yeah, and we're just talking about satellites. If any space hardware that supports astronaut life fails in space, that's extremely disastrous.
Oh yeah, no, that would be horrendous. Yeah, no, nuh-uh. Here, let's see what the next slide is. Oh, okay. Vibration testing. I actually kind of like to call it
yes.
shock and vibe, but as Karbon you'll probably talk about later, shock testing is a little bit different, so I guess it's just vibe. And when I think of shock and vibe, I think of like this cat that's like vibing out. So what exactly is vibration testing? Here, let me see if I can show this video clip. Yeah, there's not audio. There's no, yeah. So
I'll make the audio. Yeah.
So this is like a big instrument. This was actually the characterizing exoplanet satellite by the ESA. It's like an actual spacecraft. So it's basically like bouncing up and down. Does it pass the vibe test? I think this one does for sure. You can hear the audio.
That's what it's doing.
Yeah.
Can it dance right?
Yeah, so it's like vibrating at different frequencies too. It looks like it's moving a little bit faster now. You can like barely see it move. Yeah.
Yeah, it's trying to hit all those resonance frequencies.
Exactly. Well, basically this video goes on for like another 30 seconds, but so vibration testing. Here, let me move this slide over a little bit. Oop. So what is vibration testing? It is basically simulating the vibrational forces that a satellite could experience during launch. So what is going on? Why is the satellite shaking? Basically, the satellite is experiencing these like vibrational forces from a shaking table or test device. And by testing a range of vibrational frequencies, they can make sure that the shaky satellite means that nothing falls off and nothing turns on or off that shouldn't be, which can be a good simulation of like what it's like when the satellite goes up for launch. So I thought it was going to be them hitting it with hammers. Well, as Karbon will probably talk about soon, that is actually not as far from the truth as you might imagine.
That's not as far up as you think. Yeah. Yeah.
So I think this is to test more, not only structural integrity, but also to make sure that nothing just boots up.
What is it? There's a, oh man, we should have got this. There's a good video where if you shake something properly, you can actually unscrew a screw outside of its socket just via mechanical shaking. If you hit the resonant frequency just right, you can literally unscrew every screw inside a system. Pretty crazy.
What? I didn't know that. I just thought it was just to make sure that nothing would fall off.
Oh no, you can make like, let's say the screws are at a different frequency than everything else. If you hit the mode in just the right way, it will unscrew everything. And the designers have to make sure that that's not the case. They do a bunch of simulations before they even ever get to shock and vibe to make sure that there's no resonant frequencies that will, spiral into something worse. I'll let you talk about how those work though.
That's crazy. But even if the screws like really tightly fit in, then it like
yes.
What?
It can be a fully assembled, bolted down robot, and it will literally fall apart before your very eyes.
I did not know that. Yes, we are screwed. Yeah, no, that's crazy.
You better, yeah, it doesn't matter how hard you screw. It has to be designed properly.
Wow. I didn't know that. That's crazy. Well, I guess that kind of brings us along the slide, which is like, what should we check for? Well, we should make sure that the satellite doesn't fall apart. And the way that they do that is they test a range of frequencies. Typically, I'd say they go from like 5 hertz, which is quite low, to very high at 2000 hertz. And sometimes the range of frequencies, I know for like SpaceX, are specifically offered by like the space launch company to check this range of frequencies. They also check some
that's cool.
Yeah, they check some acceleration levels, which means that the satellite could experience different like G-forces based off of its like position in the launch vehicle and the specific launch vehicle being used. And they also make sure that the satellite can survive for a long duration, typically long enough to represent the entire launch process. And then finally, the satellite or spacecraft needs to be able to withstand vibrations from all 3 axes. So the orthogonal axes X, Y, and Z, to make sure that they can survive any vibration in any direction.
And if you're really cheap, you only have one axis and you rotate the satellite part.
Wait.
These machines are expensive. So
Wait,
I've seen some booty startups. They they just take the part, they rotate it. Technically, withstands it.
Yeah, and they typically like bolt the satellite to the table or the
they do.
shaking machine. Yeah. Yes.
Yep.
All right. Next.
Mm-hmm. If you go back to the previous one, I forgot to mention another fun tidbit is that solder joints in between parts inside like a PCBA board, those can actually break during vibrations.
Because of resonance?
Yes, you can break the solder joints, especially if they're hand soldered.
Do they just like crack?
Kind of yep, they just crack. And then it doesn't have enough electrical connection. And it'll just go.
At this point, what survives? I feel like nothing would survive.
It's carefully designed. Like, you have to be aware. And that's why every single part is tested. There's functional testing that goes before and after this. So let's say you have a computer part, like a computer board. You'll run a test program before you put it on shock and vibe. Then you'll run a test program afterwards. And if it changes, you'll be like, hey, oh no, something happened during vibe.
Yeah. Architelos asks, how did we ever get into space? Honestly, after hearing about this, makes me wonder.
A lot of money, blood, sweat, and tears.
Yeah.
And the fear of the Russians.
Okay, maybe at the start, kinda, yeah.
It's okay. Some healthy competition never hurt anyone.
I think that's why the rise of new startups is actually, this is my opinion, but the rise of new aerospace startups is kind of exciting because, I mean, startups, they need to be conscious about money, right? Conscious about cost. And there's also a healthy competition, although I think SpaceX is like currently the bigger one. But there's a lot of new startups that are looking into new applications for space where there is a lot of healthy competition.
Yeah, it's actually really exciting because now cost is such a main driving force. And I think people are competing for a space monopoly right now for like internet satellite base. Internet satellite's the future. Who wants stinky modem internet where you have to wire? You. So a lot of companies are competing for that, and things like trying to get geostationary orbit spots before they all get sold out.
Yeah. Yeah, but typically those, I guess for CubeSats, they typically only go for like 5-ish years before they start descending back into the atmosphere. But
5 to 20, some of them go for a while, right?
20? Is that even allowed?
Yeah. You have to get special permission, but there has been a satellite up there that has gotten an extension. They're at like 23 years right now. It's a CubeSat.
Wow, and I assume that's not just like a 1U. That's probably like,
I think it's a 3U. 3 or 6U.
Sense. And probably with like propulsion, that kind of stuff.
There's no way they could do it without propulsion, right?
Yeah. Okay, so we can take a look at the next slide. Vibration profiles. So this is a sine vibration profile. For context, I actually had to Google this. I actually didn't know this at all before I was looking at this presentation. So the satellite is subjected to individual frequencies, one at a time, and it's watching out for those resonance points, which is really dangerous. So we can sort of see this video. So it shows that at certain frequencies, you can see the middle one is really wobbly. And that's because it's actually affecting the resonant frequency that makes it wobble even more. So these are specific frequencies where the vibrations are amplified because of the satellite or its components, and it could lead to damage. Like Karbon mentioned, it could unscrew a screw or unsolder a solder joint. And so here on the left is a example of a helicopter's vibration profile. And so during a sine vibration test, the vibration waves are like swept through like a range of frequencies one at a time so that they're discrete, and making sure that nothing falls apart. So this is for a helicopter. It's a little bit different for satellites, but that's sort of what it looks like.
Oh, a good thing you may think to yourself is, how is it possible that they get all the frequencies needed? It's actually based on the rocket launch company. They have classified the type of vibrations that they see from launch conditions, and they will send those frequencies to companies who want to use the rocket, and that's how they'll know which frequencies to test. And believe it or not, they're really fun wave things that you can combine frequencies losslessly. So it's easy for you to test one fundamental frequency and another fundamental frequency, and then that theoretically also tests the superposition of the both of them.
Whoa. Yeah, no, that's some pretty cool physics right there.
Oh yes, Fourier transforms. Let's go.
Fourier transforms. Actually, I'm making a PDE series right now, and I am going to be talking about Fourier transforms. So this is a cool application.
It is one of the magic science equations. It is something that will come up all the time in physics.
It's everywhere. It's everywhere. Yeah. We got a question. If you keep in orbit by propulsion, do you have to resupply the satellite? With energy. Typically they have like solar panels that will resupply the satellite with energy.
Almost a lot of satellites nowadays do not have resupply for fuel, because it's not cost efficient to locate a satellite in like LEO or low Earth orbit and give it fuel. Because remember, launch costs are like, it's 15 million to get a rocket into space. Do you really want to get a $50 million rocket to resupply a $1 million satellite? The answer is normally no. So they just have a designated fuel lifespan of like some jet fuel or whatnot. And there are new technologies that are being investigated that convert electric only into propulsion, like plasma or magnetic. There's like a magnetic wave thing that uses the same technology as your microwave does to accelerate electrons and spit them out.
Whoa, the magnetic energy. So magnetic energy, but would it be from like Earth's magnetic field?
So you can't really get suitable propulsion from Earth's magnetic field. There's a magnetometer. It's a big like coil inside, and it uses polarities or charges to shoot electrons outside of the satellite, and it's using that as a propulsion system. So instead of using like jet fuel and you're shooting out the fuel waste components behind you, you're throwing out electrons.
Wow. No, that's so cool.
It's been tested and it works in space. It's just traditionally most people use jet fuel because, you know, Newton's, was it second law? Where it's like every force has a opposite and equal counterforce.
Yeah.
You know what I mean? If you throw something in space, you'll fly the opposite direction. And rockets are just really efficient ways to throw things into space.
Yeah, and that there's also been like ion thrusters, right? Where it's like,
it is an ion thruster.
Yeah.
It's a type of ion thruster. Yeah.
Mm-hmm. Yeah.
And there's solar sails too. There's so much propulsion technology.
Yeah. No, that's cool. I've been hearing a lot more about ion thruster propulsion recently. So that's really cool. Really cool that we brought that up. Yeah.
New thing. Yeah.
All right. Next slide. Oh, yeah, that's just the video again. Okay. So this is another type of vibration profile. It is a random vibration profile, which means that it's changing frequencies over time. So the satellite experiences a spectrum of frequencies all at once, which is a closer representation of sort of like the random nature of vibrations during launch. So what's shown here on the left is the PSD, or the power spectral density, is defined over a range of frequencies. And because it constantly changes over time, basically when we're gathering the data, the controller like takes samples or snapshots of the vibration data, and uses that to determine what frequency was being used and what the satellite encounters when it experiences that frequency.
And after all these tests, people will plug their satellite part back in and then test it to see if that part still works. If it's just a physical component, they just leave it and they're like, looks good to me, it's not cracking. But oftentimes they're like optical modules, computing modules, all these sorts of things that they need to check functionality for.
Yeah, it would be really bad if the satellite just turned on or even turned off in space.
Which all of those things have happened.
Yeah, no, for sure. All right. Next one is sine bursts, which are sudden and sharp vibrations, which simulate like shock events, like when a stage like separates from a rocket. And so the satellite experiences a sudden and sharp vibration for a brief period of time. Cool. And I think that's it for vibration testing. Do you want to talk a little bit about shock testing? We can watch a part of this video.
Yes. So shock testing is a whole nother thing. I think one chatter mentioned you might hit it with a hammer. Is that how vibration testing works? That's how shock testing works. Sometimes you bump into things and they're sudden impulses, like sudden gigantic strikes. And the best way to test something is to recreate it. And so you want to play it.
Yeah, here, let's...
Vibration test. And
okay, here, let's
provide
go.
shock testing that delivers mechanical shock to the test article.
That's a cannon.
That's a cannon.
That's a
impulse
gigantic cannon.
Article.
They are blasting a metal component at a satellite piece. That's what they're doing.
Yeah.
And in actual day-to-day use, because the cannon is pretty manual to reload and whatnot, this is more of a university research setting. In industry, they have a gigantic hydraulic battling ram that just kaboom and smacks into the satellite.
Wait, literally they're doing that right now. Yeah, in the video.
Heck yeah. Yeah, that's what they do. So yeah, someone's job is literally just trying to break things with massive amounts of force. And I'm sure they're very happy. Oh, also ear protection. Ear protection is very important.
Yeah, no, I assume that's very, very important. But that's so cool. It's literally, I did not know about this until you showed me the video, like before our stream started. And I was like, that's a literal battering ram. Like, what?
Oh, yeah. And it's great. I've seen some janky university setups where, because they don't have the full setup, they'll just stuff a bunch of gunpowder and then launch like a medieval cannon against their satellite. It's pretty funny.
Hairday says, I wish it was my job to break things. I wish it was my job too. That's so funny.
Oh, if you are in environmental space testing, your whole dream is to break things. You are tasked with a ton of money and time, and you say, and people tell you, I need you to try to break things as best you can because space is gonna do it better. So give it your best shot.
Maybe I gotta, like switch careers, and just go into space environmental testing. I'm no longer a physics VTuber. I'm no longer astrophysics. I am actually just smack it really hard. Okay, that sounds really sad. I meant destroy things VTuber. Destructive VTuber.
Oh, we'll talk about single event effects later. That's something that I forgot to add in the slides, but we'll add it to the end.
Ooh, yeah, I'm curious to learn more about that. Here, let's see what the next... Oh, that was just the video. Oh, okay, so I guess this was actually one example of a shock and vibe, like, plan that was used for the European Space Agency. It was like a specific specification. And what it's showing is like different tests within a full study of vibrations. And so you can see that there's different directions, there's different levels. You got to do like high levels, and then you also could do the random vibrations and not just a sine sweep. So sine sweeps are for like specific frequencies. And within each of these, they also have lower level sine vibration surveys to make sure that nothing's going to fall apart. So this is just one example of the vibrations studies that are conducted on spacecraft before they launch.
Mm-hmm.
Oh, wait, I think we just got a raid. Hello?
You can get raids in
Well,
YouTube? Really?
Yeah, you can redirect. Hello,
Oh
CL.
my.
Thank you so much for raiding. Oh, it's a Ramadan raid, even more special. Thank you so much. Hi. Well, for those of you who came in, we are talking about space environmental testing with Karbon. And we both do IRL physics work, so this is really cool.
Two IRL physicists.
Physicists.
Physicists. It's early for me. Doing space VTubing. Let's go.
Let's go. Science VTubers, rise up. Yes.
I see. Is CL do coding stuff?
Yes.
Uh-oh.
CL
They gotta
does
watch
coding.
out.
Mm-hmm.
We're gonna scare them with our single bit errors. We're gonna talk about how the sun destroys computers.
Oh no! Wait. Oh my god. Oh yeah, with bit flips and everything. Well,
Yep,
we will save that for the end. But yes.
Yes.
Here. Next up is acoustic testing. Maybe you could talk about this.
I love acoustic testing. So the thing is, if you go back one slide.
Oh.
Yeah, I want to tell them about this. So you see each one of those black boxes? That's actually just a regular concert speaker. It's one of those things that you see at a band, and you get a ton of them, like 20 of them, and you point at a satellite in between, and then you amp up the volume. The reason is there are two different types of vibrational failures. One is mechanical shaking, like earthquake type of shaking. Something is shaking mechanically, and that's transferring through a physical solid. The second type is transferring vibrations and energy through pressure differentials that happen in fluids, aka air. Air is a fluid. It's how we do all the fluid dynamics modeling and all that stuff. It's done with air. And so you can have peaks and troughs in the air pressures, and that's the exact way. If you go to the next slide.
Mm-hmm.
Yeah, you see that glass right there? That's how opera singers, they break glass. They can hit a certain pressure resonance frequency that just shatters glass. And this will also apply to physical metal slabs. You can also break things with sound waves. And I don't know, there's a couple supervillains in Marvel DC comics where they're using sound waves to break things. This is one way you can do it. And so the rocket makes so much noise, so much sound comes from it, that we have to test to make sure that that sound does not break anything inside it. And the one way we can do that is to get a bunch of concert speakers, model everything, and then blast it with a full range of sound waves. It's the exact same as vibrational testing that you saw before, with the whole like sine wave sweeps, testing different frequencies, except instead of mechanical shaking, now we're using sound.
Wow. Yeah, no, the satellite Chan is listening to J-pop. No.
Oh, so one of your chatters, they mentioned a great thing. There's no air in space. Correct. You are right. Sound testing only matters for launch conditions. Once we're in space, don't care. It's fine. But in the Earth, while we're getting into orbit, that's where things break. That's a really high failure point. So that's what all this modeling is for.
And that's a lot of, launches are loud, and that's a lot of like energy and whatever. My brain is struggling to function, but they're loud, and that's why the acoustic testing matters for the launch conditions, right?
Yep.
Yeah. Cool.
We can go to the next one. Let's see what's next.
Thermal vacuum.
I have a personal love-hate relationship with TVAC, thermal vacuum testing, and I'll explain to you why. So if you're not familiar already, space is an inhospitable environment, both in temperature and vacuum reasons. Okay, if you go to the next slide, we're gonna learn some thermodynamics. All right, number one, if you didn't know, space is really cold, like really, really cold. why is it so cold? A lot of people wonder, why is it like, I don't know, what is the space temperature? It's like minus 220 degrees Fahrenheit.
2.7 degrees Kelvin.
Thank you. Oh, wow. That's actually pretty close to absolute zero. Yep, it's very cold. The reason why it's cold is something that people don't really think about that much, and there's no particles in space. It's a vacuum, and that's why it's cold. Vacuums are inherently cold because particles transfer energy by colliding into one another. If there aren't that many particles to collide into each other, heat transfers very poorly, aka everything just kind of radiates its heat away through electromagnetic radiation, and meaning things just don't bump around. Even if I had a heater out in space, none of that heat would actually reach me because there's no air molecules between the heater and me to transfer that heat over. So everything's just freezing cold.
It's like 1 hydrogen atom per cubic centimeter.
Yep. All right. And if you go up another slide, so even though it's really cold, it's also really hot. The reason is there's no atmosphere. Again, there's no oxygen molecules, no carbon, like nitrogen and stuff in the air that will absorb the heat and then spread it around. And the sun is a deadly, not laser, it's a black body radiator, all right? Lasers only emit one wavelength of the spectrum. I'm sorry, Bill Wirtz, a great funny video, but it is technically a black body radiator. I will live and die in this hill. Science will agree with me.
The rage in this statement.
Yeah. And so when you go from darkness, near absolute zero, and then you see the sun, and the sun's hitting you with its full electromagnetic spectrum without an atmosphere to kind of soften that blow, it will instantly go to boiling. It will go like 200 degrees Fahrenheit instantly. So you're going from near absolute zero to suddenly swinging to over boiling, way hot double boiling temperatures, which is crazy. And you need to be ready for that.
Yeah, so I guess in chat it says, Spaceman RIB says, thermal gradients can be insane. It's hot if you're facing the sun. Yeah, no, exactly.
You're curious how a spacesuit protects from all of that? Lots of insulation. We'll go into it. I'll explain in a moment.
Here,
What's next? Yes. So those are really crazy extreme conditions. That is super difficult to do on Earth. Very rarely anywhere will we ever see swinging from the hottest hots to the coldest colds within the time span of seconds, right? And so how that's done and tested here on Earth is we use conductive electrically heating elements. So we'll put some metal plates, throw some electricity through it, and let it bake in essentially just a big fridge. And then when it's time to cool, thankfully, liquid nitrogen's evaporating temperature is low enough to get to that minus 200 degrees plus Kelvin. Or not Kelvin, Celsius. You can get it pretty low. And so we can just dump a bunch of liquid nitrogen on things, and then we can also heat things up in a big baker oven. Now, that would be great, but it actually gets more complicated than this. If you go to the next slide.
Oh, this is a little last. Yeah.
Time to learn about thermodynamics and some cooling suits. So, there are 3 types of ways that heat can be transferred: convection, conduction, radiation. Okay? The image is a little misconstrued, so I'll just go through them really quick. Conduction is through contact, metal contact from something else. You will get heat transfers. If you heat one side of a metal like brick, it'll heat the other side as the heat transfers through. That's conduction. It's conducting. The other type of heat transfer is convection, where when you have a fluid, aka air, or in boiling water, the hot molecules will rise through the top, right? The thing is, though, there's very little molecules in space. It's a vacuum. So conduction, sorry, there's nothing to conduct. Like, there will be some conduction through the metal contactions in the satellite, but that's it. And then convection, there's no particles. Sorry, convection's not happening. And that leaves the third form of heat transfer, which is radiation. And that's purely based off of electromagnetic radiation, meaning something that I don't know. How familiar is your chat with quantum mechanics? Like, do they know about the photoelectric effect?
Well, I think it would be best to sort of explain it just in case somebody in the chat doesn't know or is unfamiliar with it.
Okay. I'll explain it just in case this hypothetical like Timmy walks in, but I'm sure you all know about the photoelectric effect, right? Of course. The effect where if you excite an electron and it'll go up one energy level and then it'll drop down and then it'll send out another electron. It's one of the basis of quantum mechanics where you have discrete energy levels, meaning atoms can only accept photons that are of this energy packet size, a specific frequency. But the thing is, what if it's the wrong size or it's close? You know, what happens? What happens is it actually heats up. And that's the radiation heat. So you get radiation heat anywhere in space. That's how the sun is actually conveying its heat to you and to us. It is sending out light that bounces onto us and heats us up.
Yeah, no, that was a great description, especially for people who are not as familiar with how exactly the quantum mechanics of all of this works. But yeah, no, that's cool.
Yeah. The reason why I critique this image slightly is because when you see radiation like this on the image, you assume that it's like the heat that comes from a fire when you put your hand next to a fire. Not entirely true. The heat that comes from a fire that you feel is mostly actually carbon molecules that are heated up that you can't see, or air molecules that have touched the fire and then it's hitting you with convection currents. It's not truly radiation. Radiation is actually a very terrible way to send energy. The problem is you cannot test a thermal element without making sure it's in vacuum first. The reason is that let's say something is in vacuum and let me think about it. Okay, let's say you want to test something to see if it can withstand really hot temperatures, right? Like a PCBA board. You heat it up on Earth. It works, it's fine, it has good cooling units that are able to disperse the heat, but then you take it up to space. It's in a vacuum. It no longer has convection currents. There are no air molecules in space. Those air molecules were actually helping to transfer the heat, and that's not happening anymore. And now your PCA board fries itself in space, and you never knew, even though you tested it with the same temperatures on Earth. So you have to test in vacuum.
Yeah, and for context, the PCBA board is like a circuit board.
Yep. And it's also especially painful, and the reason why it causes me a lot of pain is these TVAC chambers that heat and cool down the testing unit that you're trying to throw in there. It takes so long to do it, like literally ages, sometimes weeks to get up to temperature. Yeah, it takes that long. Like those gigantic ones that a person can fit inside, at least weeks, guaranteed, maybe even a full month to get that thing up to temperature, because there's no air molecules. How do you get it hot? You have to you're heating it up by shining lasers onto it. Like that's what you're doing. You see that?
What?
You see the metal plate in the middle? That is the only heating element inside it heats the entire plate. Okay, like the bottom plate with conduction. So they're conducting heat through it. The problem is the rest of the satellite components, right? They're not directly touching it. They might be directly touching other components of the satellite, but they don't get up to temperature. But the space requirements require that you test every single component up to that heat. So you literally have to wait for the heat to radiate off of that little metal plate to every component inside the satellite. And it takes a really long time. It's the major bottleneck for almost all environmental testing.
What? Yeah, no, Spaceman RIB says 9 weeks is our record. That's crazy. I didn't know that. What?
Yeah, it's really long.
And is this required
pressurized
for all? Because I know for like CubeSats or smaller satellites, they don't require this testing.
Do they not? Really?
From my understanding, it's only really the shock and vibe testing. I don't know. I probably am not. I'm not the most knowledgeable on this topic.
To be fair, you are only required to do this based off of your risk tolerance. Like, how confident do you feel that your specific motherboard or your component will withstand thermal vacuum, right? Who knows? If you are confident about your specs and your design, you can skip it. You don't have to do this.
But is it like
It's just an
required
expensive
by
bet.
space like policy, like regulations, or by the launch service provider?
It can be required by launch service providers, but this type of failure is less required because the launch service provider, aka the person who owns your rocket, doesn't actually care about this as much. Once this fails, it failed in space. It's outside of their rocket. The reason why they require things like vibration testing inside the rocket is they don't want your component to break in the rocket and then take down everything else that they have in their payload. That would be really bad. They don't want that. So this only happens once they already launched the payload and they don't really care about you. They're like, hey, if it fails, that's on you.
Yeah, I mean, that makes sense. I mean, it's really up to the confidence of the designer, the builder of the spacecraft.
Oh, there was a good question in chat. Can you make the chamber smaller? Yes, you can. Some components of the satellite, though, are freaking massive. Or not satellite, just anything you send into space. Some of them are really big. And if they're really big, you have to test the whole thing. So the larger the chamber becomes, the harder it is to test. It takes longer to do.
I wonder how they do that for like James Webb, like these huge telescopes.
They just chuck the entire thing into a massive TVAC chamber. It's like the size of a building.
And that would take like months.
Yes, you are correct. It takes that long. And then someone will be like, oh no, I forgot something inside. Can you like open it?
No!
And then you're like, oh no, that's terrible.
Oh, wow.
Yeah.
That's crazy.
It's pretty wild. Oh, and just some added complexity, since we're literally talking about one of the hardest physics concepts, which is thermodynamics.
I agree
Another
with that.
thing that yeah, it's hard. Another thing that throws a wrench to this problem is there's a phenomenon called degassing. When you are putting things in vacuum, what will happen is, let's say you put some special black paint on your satellite part. As you reduce the pressure, that paint may spontaneously go from a solid into a gas and then float around and mess with things on your satellite itself, and also screw with the chamber. It will like block different ports, get things clogged, mess with sensors, give you bad readings, all that stuff.
Wow. So what about like rocket testing though? Because they have like paint on the outside of that. How do they make sure that
They have to classify it. They do material analysis, and then they do degassing tests on it, where they put it through vacuum chambers and then see how much matter comes off of it.
Oh, rip. Yeah, no, nothing like the unforgiving vacuum of space. All of this talk makes me wonder how we even made it into space in the first place. I mean, all of these tests mean that at some point something bad happened, which is why they need to be tested, right? So.
And Chad is right. There are people who pre-outgas their chips before they send them to space. Because once you outgas, the next time you outgas, there'll be less, because you've already done it once. And so they'll pre-outgas things.
Oh, but like how much less? I guess it varies from material to material.
It does. And that's the worst part, because you don't know.
Yeah.
Right? That's the question, the money question.
Wow, that's crazy. Well,
That nothingness causes problems. You know what? That's a banger video, Z. I can't wait to see you make a video calling nothingness cause problems and then rant about the vacuum of space.
wait, video idea? Wait, that would be
Video
so
idea,
funny.
let's
Nothing.
Yeah.
I'm gonna jot this down. That would be absolutely amazing.
Oh, yes. Epoxy is awful. I'm sorry. You cannot use epoxy in any spacecraft. That is a bad idea.
Yeah. That's why the first satellite was just a steel ball in space without paint. Well, I don't know if back then they knew about like degassing.
Degassing? I think they did. I think they were aware that it was a problem. it's like a known phenomenon in low pressure environments. Though there's so many things that can combine here that can cause issues. Like if you had asked me, hey, can't we test if the satellite can work in a vacuum separately from the heat, from like heating it? I would have said yes in like with my naive impulses, like, oh, you can test those independently. And then you find out you can't test them independently. You actually have to you have to do them at the same time because the heating thermodynamics is different.
Yeah. Wow. Well, this was so detailed. You know so much about this. I think that was actually the last slide.
Yes. Bonus slide for my Code Life raiders. There's, we didn't touch on this.
Bit flips.
Bit flips. Radiation testing is a thing. So for electronic components, when something hits your electrical component in just the right way, it has enough energy to actually flip your bit from a 1 to a 0. And that can break a lot of things. And so there is, for things like cameras, photo sensors, anything that has like electrical programming units, even if it's internal, they need to be put essentially in a radioactive chamber that tests to see, can it withstand the radiation of space? Like literally we're blasting with a cancer ray. It's like a cancer gun that you point at your computer chip and then you see if your computer chip can handle the cancer gun. And oftentimes there's software redundancy and then hardware redundancy. Intel specifically sells base rated computer chips that have copper outcoatings or lead protective coverings that will cover the main memory portions to prevent and absorb those high energy radioactive emissions from things like our sun and other stars, and even like crazy space events like freaking black holes merging.
Yeah, I mean, I heard for... Oh, wait, go ahead.
No, go on.
I was just going to say, I heard for the Europa Clipper spacecraft, it's heading towards Jupiter, which has like the strongest magnetic field other than the sun. And to prevent the components and the instrumentation from being harmed by that radiation, most of the instrumentation is in this like safe box on the side of the spacecraft, which is protected from the radiation.
Yep. And it protects it from the radiation through what's like it's called a Faraday cage. Essentially, it's not a true full Faraday cage, but it absorbs the electromagnetic radiation from using a conductive layer of the electrons on the outside of a metal, or it also just absorbs the physical force of like an alpha decay or something like that. If you have a thick enough material, which I don't know, copper, lead, they're very dense, it can absorb a lot of that. And so that's how we handle it physically. But there's also software things like if you didn't know how the internet works right now, when we send packets of information from one computer to another computer on the other side of the world, that's actually unreliable data transfer. And so there's a bunch of things that are done to ensure that there are no bit flips that occur from one internet communication from one side of the earth to the other. And there's like, I won't get into the math of it, but you essentially just have a padded list of ones and zeros, or a bunch of ones, and you check on the other side, did any of them flip to 0? And then if so, then you're like, ooh, a bit flip occurred.
Wait, I have a question for you.
Yes.
What happens if a bit flip occurs and it affects like the software that does like the upload, like the downlink, uplink of information?
Bad. It bricks the satellite uplink, downlink.
Yeah, because you wouldn't be able to communicate with it, and it wouldn't be able to communicate back.
That has happened, and that's why most computer chips specifically, like if you have a motherboard, to prevent really, really bad RNG, like super bad luck, there's multiple motherboards that are fully independent, or computer chips, memory sticks, the graphic processing units, everything. They're fully independent from one another. So most satellites won't just have one computer on them. They'll have like 2 or 3. And if one of them goes bad, at least you can communicate to the other one, and then you can push information that way.
And would just one bit flip do that? It could, right?
It can. But the designers know that this is a known issue. They are expecting it and design the system architecture to prevent it. I mean, there's a really famous example on Earth anyway. There was one bit flip that occurred for an election in some European country, some small European country, and it changed someone from being the last place in electoral vote to the first place because it bit flipped the the biggest number, and it gave them an extra like 12,000 votes instantly, just boop, and that can happen. Yeah, it was from the sun. It was they tested everything, the hardware, nothing has changed the code. It was in the memory stick of the voting machine. It just, act of God.
Yeah, and these bit flips, I assume they would happen more often during periods of greater solar activity where the sun is sending out like solar flares. Is it possible for there to be like a wave of satellites being hit by like a solar flare or like a solar storm that just like changes all of their bits then?
Oh, like a bunch of them all at once?
Yeah, like all at once.
Yeah. Also, someone in chat mentioned it. It was in Belgium. It was a Belgian election. Thank you. Yes, it's mentioned in a lot of computer architecture books because it's something you have to anticipate. Actually, the thing that causes bit flips is not as much solar radiation from the sun. It's from more extreme events deeper into space,
like cosmic really rays.
Cosmic rays, like from the creation of the universe, is a little too low powered for that.
No, from like black hole merger type.
Yeah, like phase. What are they called? Crazy celestial events, super far away, will send out really high energy electromagnetic waves that will mess things up. It has to be from a crazy event, like black holes merging level thing. So some black hole merged, I don't know, 20,000 light years away, and it can bit flip you here on Earth and cause problems. It actually gave a Mario speedrunner like plus 10 seconds to their time.
Gamma ray bursts, yeah.
Yeah. Gamma ray bursts, thank you. A pulsar, yes.
Yeah, and these cosmic rays they're intense. Like compared to like a solar flare, they are much more high energy. And apparently a lot of these bit flips come from the alpha radiation from inside the chip.
Okay. Another thing, yes, sorry. Since we're on the topic, the computer chip, if you make it out of radioactive components, yes, you will cause bit flips. I'm sorry, don't build your computer chip out of uranium. Also, don't mine your computer chip metals next to a radioactive place. It has happened. It has caused issues. There's been someone who's launched a spacecraft into space using a computer chip that has radioactive elements inside the computer chip that caused it to bit flip. So even though everything else was shielded, it still had issues.
Oh, that sounds like the worst thing ever.
Yeah, it's pretty bad.
Yeah, no, that's pretty...
You have to secure your supply chain, and you have to like get some Geiger counters, test your computer chip.
Wow, no, these things are crazy sensitive. Yeah. The calls are coming from the sun.
I would say it's not that it's super sensitive. It's because it has the opportunity, the potential to ruin everything. And that's why it's scary. Generally, like day-to-day use, if you bit flip in your computer, there's a bunch of redundancies put in place that you'll rarely see it. But if you're in space, if that one error hits just the wrong way, it can ruin your multi-million-dollar decade plan.
Yeah, and for something like Europa Clipper, like they are only sending one of those up. And that's like thousands of people's like lives work. And it's going to take like 6 years to get there. Like there isn't going to be like another one. So it's important to get it right.
Yep, I agree.
Yeah. Well, I think we're almost coming up at the like 15-minute mark. If anybody has any last-minute questions, please drop them into the chat. It looks like
if you didn't get to a question.
Spaceman RIB also says that shielding design and mitigation is their thesis. So thank you so much for stopping by, and yeah, it's pretty cool.
We hate bit flips. Get out of here. Go away.
How about testing for weightlessness?
Oh, like zero gravity? You know, most testing for weightlessness is actually not needed. Weightlessness itself is generally okay. It's also covered in vibration and shock. So if you ask yourself, what is weightlessness? Weightlessness is just falling. You know, you're just you're falling in sync with gravity. And so as part of the vibrational and shock testing, there will be periods where you are weightless. And that's how it's tested.
And then favorite celestial object, Karbon.
Oh shit. My favorite celestial object? You know, I'm a basic boy. I like our sun. It's very nice. It's a yellow star, one of the best stars out there. If our sun was a red star, we'd have no atmosphere. So thank you, yellow sun.
I mean, it would be really cold, and even if we were, we actually had a talk on exoplanets, talking about how the TRAPPIST system is like in the habitable zone, but because red dwarfs are very active, and because these planets are like all within Mercury's orbit. Yeah, so it actually would like fry their atmospheres.
Even if you're in the habitable zone, it doesn't mean your exoplanet is habitable, okay? The star health matters a lot.
Yeah, no, exactly.
Red stars, they just cooler, so you have to be closer to the star to meet the same temperature. But they're also unstable, so you get your atmosphere evaporated away from all the solar flares.
Yeah, no, I feel like habitable zone like is what is considered the most, but there are just so many other factors to what determines a place to be habitable, and if it's being fried by radiation, it is 100% not habitable.
Oh, I see a question from Nikki. Nikki Fergan asking about how you test JWST unfolding on Earth. There's like satellite essentially they're satellite arms that remain closed until you launch it, and then once you launch it, those satellite arms spring out so that you can test that mechanism. Usually that's done is there are a bunch of springs that just push the solar panels out, and they're tied down with like some twine, and then you burn the twine when you launch in space. That's actually pretty simple. In the final integration part of satellites or any other component, they'll just burn the twine, see it spring out, and they'll be like, all right, all good, and they'll put it back together.
Yeah, the burn wires. Yeah, that's cool.
Yep.
Actually, there's like a whole field of study related to space origami. I actually heard I heard a talk about this like maybe like a year ago, but there's people who like study the way that these like spacecraft unfurl themselves, and in the case of like a giant like solar shield or a solar shield, you need to be really cautious about like how that is like folded up and how it unfurls in a way that's cost efficient, so it's like lightweight but also like does its job.
Yep. And those things unfurl a lot. Like the solar panel component of the satellite is usually the largest piece and can be literally like 80% of the volume. So, or surface area.
All right. Quick question from Dan. I think this is our last question. Do you like tardigrades?
Like the space bears, not the little guys.
Tread carefully, by the way. This can hurt potentially or benefit my perception of you. I'm just joking.
I mean, I think they're cute little guys. I wish I had their radioactive shielding though. That'd be nice.
What do you mean that they're cute? What?
Do you not think they're cute? They're like little guys. They're a little chunky. They have like double chins. No?
I'm terrified of space bears.
Why? Why are you is it because they're so resilient?
No, it's because they look weird.
They're adorable. The looks, I keep them as a pet.
Ooh! Well, okay.
I have a nice jar of them right here, right next to me. I'll show you later.
Wait, do you actually have them?
They're everywhere. I think they're just present all the time, yeah.
You can buy, like, frozen ones, I think, though, for testing.
Oh. They're still alive if they're frozen, aren't they?
Actually,
that's the worst part.
When they are not exposed to enough food, they can actually choose to freeze themselves. Like, it's like their state of hibernation, basically. And that's why they can survive, basically, anywhere. They're on your face, like, too. Ooh!
Don't think about it. Don't. It's the one thing you learn very quickly if you do any sort of physics study is don't think about things too deeply, or you will have an existential crisis. Just at some point, you got to draw the line and be like, you know what? God does roll dice.
Yeah. Sometimes I think about, I don't know if you know about this, but it's like the vacuum decay, free vacuum decay, that there might be like a bubble with like different physics inside of it that's just expanding. So like it's expanding at the speed of light. And so it would just like all of a sudden just like, we wouldn't even see it coming. It would just like hit us and then it would just be like darkness. But don't think about it too much. I had to instill you with fear because you have instilled fear within me about tardigrades.
Thank you. Thank you for reminding me about the vacuum bubble. I put that in a little box. Now it's coming out.
Well,
yeah, existential crises. If you like having existential crises, I recommend studying physics.
Next collab, existential crisis.
New ASMR video. Karbon reads you a bedtime story about the end of the world, heat death of the universe.
Oh no. Wait, that would be kind of funny though. Yes, Karbon is indeed baking the good stuff. Exactly.
Oh yeah. Yeah, it's been fun. I wonder if y'all learned anything like super fun. Did any of your chatters be like, oh my gosh, I didn't know this. This is crazy cool.
Yeah.
I think the funniest bit for me was the I love the shock testing. I'm sorry. I like that they have essentially cannons and gigantic battling rams.
I think for me, the craziest thing was like how much vibration testing actually affects a satellite. Like I didn't know you could like unsolder a joint or unscrew a screw. I thought those are pretty in place. Makes me, and that was really cool. And the battering ram, that was also equally cool. Maybe chat, if you have your favorite moments, you should drop them into the chat. But yeah, no, I'm so glad we finally made this collab happen.
Yes, it's fun. I like nerding out too, and it's fun to talk about how space is an uncaring void. I want to educate other people so that they feel my frustration. So when I come talk about space and I like angrily shake my fist up into the air like an old man, you know, people will agree with me. Okay, it's unreasonable. Come on.
Well, we definitely have to run back a collab sometime. Maybe we'll do one on existential crises or, I don't know, space bears. Who knows?
Tier list existential crises, physics crises.
Physics crises, or
wait,
maybe even Kerbal.
Or Kerbal. We could also play a game. Yes. Wait, I'm just kind of thinking about moments in studying physics where you have a crisis or like a brain fart and you're like, I don't understand how this is possible, and then we rank them. That would be funny.
Wait, that would be so funny. We gotta run this back. Yes.
Yeah, the Fourier transform actually broke my brain the first time I learned about it. I was like, excuse me, how? Huh?
Yeah, no, it was the first time I learned the Fourier transform, I was like, what is this ever going to be used for? And it's just so everywhere.
It's annoying. It's annoying that it's everywhere.
Wait, I love the Fourier transform.
Yes, it's good. I have a love-hate relationship with it because I did some quantum mechanics at one point, and you can apply the Fourier transform to positional space and temporal domains as well. Like that, it gets complicated, especially when you're talking about quantum particles and light.
I have to say, quantum physics is probably my weakness. But when I'm thinking Fourier transforms, I'm thinking like, you know, partial differential equation, like numerical methods, like predicting what a heat system's going to look like in X amount of time.
That is true, but there are things like image display analysis is a whole field where they use Fourier transforms. So in order to characterize if a display is good, they'll actually look at an image with a certain pattern, and then they'll look at the Fourier transform of the image in like a 2D thing. And you have to be able to flip a Fourier transform of a like spatial image, like what you're seeing on the screen, into a frequency domain in your brain, like on the fly, is very common.
Wow. Well, I fortunately have not had to encounter that, but that would be real. I would not be able to do that. That sounds really intense.
It was a learning curve. Those people are cracked. All right, Worst part about doing science is you meet other brilliant scientists.
and it's the best part. And it's the best part.
No, they need to be less brilliant than me, all right? It makes my job too hard. The self-doubt.
Oh my god. But Pawchamp Senpai says we need another collab. It works so well. Yes, we definitely need to. And yes, we will run this back. Karbon is amazing. Yes. Oh wait, no, it's Captain is amazing. Well, I think Karbon is amazing as well.
Thank you. You know, I can't compare to Captain, but I'll try my best.
I think we should wrap up because I do need to head out. But if you haven't already, Karbon's Twitch link is in the pinned comment. So go follow, I guess is the correct term in the Twitch language. And
Karbon VTs, all my socials. You can just Google Karbon VT. I made a website that is algo based to get on top of Google search ranking. So please.
What?
Long story short, Google ranks how quickly you are recommended based off of the website optimization, like how quickly the web page loads. So I did a bunch of jank on the back end to make it load faster.
Oh my god.
It's silly, but anyway, Karbon VT. I'm an astronaut VTuber. I do science sometimes. I also do silly things. I'm currently on a Monster Hunter binge, and I may not see the light of day for a couple weeks.
Well, hopefully you will see the light of day once more so that we can run back a collab. So, yeah, okay, I think we're about time. So, thank you all so much for joining. This was so much fun and also a really cool learning experience. I learned a lot. I hope you guys learned a lot too. Thank you all so much for joining. I will maybe see you guys next week. If not, I'll see you next Saturday for the collab with Nep. And yeah, I will see you guys in the next one. I don't know, Karbon, if you have like a...
See you guys? Oh my.
Do you have a little like slang slogan thing?
No, I just play the song closing time and I tell everyone to get out of here.
All right, chat, get out of here.
Have fun. Thank you for having me.
All right, well, in that case, get out of here. I'll see you guys in the next one. Bye-bye. Boop.